For more than 100 years, Schneider Electric has been an industry pioneer of market-leading solutions. As the engineering landscape rapidly changes, no one feels the impacts of the mounting challenges like consulting engineers. We understand these challenges. We face and solve them with you every day. Projects are becoming more complex, faster moving, and the connected world demands immediate answers while margins grow tighter. As an expert in your own right, we're set on making sure that you're equally matched in the manufacturing company you turn to, which is why we're launching Proficient for Consulting Engineers, a suite of services and tools that gives you unparalleled control from design to implementation, solidifying a real connection between highly qualified professionals. Proficient is built on a foundation of E2E, or expert to expert. Through innovative technology, responsiveness, and industry-leading BIM advancements, Proficient is tailored for you. All backed by market-proven Square D and Schneider Electric products with matchless service and support, we're delivering expertise that enables you to excel. You spoke, we listened. Proficient for Consulting Engineers. Expert to expert.
Welcome to Consulting Engineer for Proficient for Consulting Engineers webinar series. On today's topic is on distribution transformers and the DOE impact. Today's webcast is sponsored by Schneider Electric and its various brands. I'm your moderator, Wendell Leisinger, Consulting Engineer Segment Manager for Schneider Electric. Please note that it's really important that you join our portal. Joining the Consulting Engineer portal gives you the opportunity to get continuing education. Also, it's going to be where you're going to get your certificate of attendance for today's PDHs. Also, it gives you direct access to layout tools, design tools, building information models, and other tools available for you. Likewise, it gets you an update in the latest information and products and applications for your particular designs. And also, you'll be able to access our new program, Experts on Demand, when questions arise. A little bit of housekeeping for today. How to ask questions. On the portal, on the webcast portal, on the bottom left-hand corner is a note that says make a comment. Click that and then ask your question, and those questions will come to me as the moderator, and I will periodically bring those questions to our presenters. Notice that if you want a copy of this particular webinar and the presentation itself, you can go to the top right-hand corner to the presentation download and download it. Also, please note that if you've registered today, your certificate, when you go onto the Consulting Engineer portal, may be 48 hours before it's available. But if you've pre-registered prior to this time, it's available 1 hour after the presentation. The information is in this particular slide. And last, but probably most important, is a survey. The bottom center of your screen, top center of your screen, is a survey button. Please feel free to fill out that survey. Remember to fill it out before you exit, and we'll get your feedback, and we'll continue to make Proficient for Consulting Engineer webinars better for you as we continue with this series. Today, the course objectives are to understand the background and history of what's gone on with energy efficiency as it impacts distribution transformers, low voltage and medium voltage. Also, you'll understand some of the things that are impact from a manufacturer perspective around form, fit, and function that we had to do as manufacturers to meet these particular demands by the DOE. Last, there will be additional information on codes and other requirements impacting distribution transformers. With that, I'd like to introduce our presenters today. First presenter is Janice Fuller. She's our offer marketing manager for medium voltage transformers here at Schneider Electric. Our second presenter is Thomas Patzner. Tom is the product manager for low voltage transformers here at Schneider Electric. With that, I'll turn it over to Tom.
Hello, everyone. The 1975 Energy and Policy and Conservation Act is where the government started to evaluate commercial and industrial equipment. The distribution transformers were included in this act. There's been 2 amendments to the act since the initial, one in 1992 and one in 2005, that addressed distribution transformers. It is critical to remember that it did start in 1975 because, as Janice will point out earlier, there was a court case, and it was the 75 processes that were actually the basis for the court case. In 1992, that amendment to the Policy Act actually gave money to the Department of Energy to start to analyze distribution transformers to determine if efficiency levels were justifiable to be set. The market responded. The EPA created an Energy Star program for distribution transformers. The National Electrical Manufacturers Association also responded and were proactive by actually setting levels for this Energy Star program that were above and beyond what was readily available in the marketplace. Once that Nema standard became readily available in the marketplace, which was 1998, a number of states started to mandate those levels for their levels of efficiency for low voltage. Why were low voltage transformers being mandated by the state? The reason is the industry was actually creating extremely high losses in their transformers. And if you actually look at the 2004 release and the analysis, which was available to us manufacturers long before 2004, they were actually predicting the low voltage transformers would continue increasing their losses. So the reason the state started to mandate it was to stop the low voltage manufacturers from making a product with increased losses. The Department of Energy started their process in approximately 2000. And by 2004, they actually had the first rules called the advanced rules, and they actually published their first deep dive analysis. At the same time that the DOE was working on their analysis, an Energy Act was also going through Congress. This Energy Act ended up being the 2005 Act, but it actually was originally called the 2002 Energy Act. The difference being is the government actually worked on the act for 3 years before it became law. In this law, the distribution transformers low voltage were actually set to the TP1 levels for efficiencies. The law actually also gave the Department of Energy the authority to set the levels for medium voltage, and that was due to the findings in their initial analysis, which was published in 2004. The market did have to reply to this, and one of the things that occurred is because the low voltage were set with minimum efficiencies equal to the Energy Star program, the Energy Star program was disbanded in 2007 to align with the fact that the law was now equal. The other thing that occurred is the Department of Energy stopped looking into low voltage. So even though they had their initial analysis completed in 2004, they did not go any further with the process due to the fact that low voltage was set by law.
So the DOE also finalized the medium voltage transformer requirements as well. The final rule from 2007 mandated efficiencies required in 2010. After 2010, several states and special interest groups filed lawsuits requesting the DOE to take another look at the efficiencies. The DOE agreed to not lower the efficiencies, but to look at the efficiency requirements. And that's why we're here today. We have now new efficiencies required for the Department of Energy, starting for shipments in 2010. They also included how to test distribution transformers. They have 3 ways to test. There's a basic model, a sampling plan, or an alternate method that the manufacturers can decide upon. There's also penalties if the manufacturers are found not to comply with these standards, up to $200 per day until they have rectified the issue that if they are found to be non-compliant. It is a self-policing, so someone would have to find if the manufacturer is not compliant. But there are penalties if we don't meet these new efficiency requirements. So what is a distribution transformer? For medium voltage, it's a 2500 kVA or less rated capacity, 34.5 maximum voltage on your primary, and a 600 volt class secondary. So 5 kVs do not apply, above 2500 kVA do not apply in this requirement. For the liquid fill, it's a liquid immersed. So liquid immersed is mineral oil, seed oil, less flammable fluid. And for a low voltage distribution, for dry type, it would include our VPI style or a cast coil style.
The Act also defined low voltage, and there's a big difference between the low voltage distribution and the medium voltage distribution, and that's here in low voltage. The input voltage is 600 volts and less. And the big difference here is if you look at the medium voltage definition, that can only be a step-down device. 34.5 is on the input, 600 is on the output. So if you are specifying step up in medium voltage, those products are not included in the definition and are not included in the law. However, in low voltage, because 600 is the input and 600 is the output, both step up and step down transformers are included for the low voltage offering. The other thing that the law covered is product that is not considered distribution transformers. This is the current list. It was actually published in 2005. Since 2005, only one other product has been added to the list, and that is mining transformers. The product that is added to this list are products that will not give the Department of Energy large amounts of energy savings if they were mandated. So if you look at these products, for example, number 4 is a machine tool or control transformer. Most control transformers in the marketplace is a 200 VA device. If they mandated a 200 VA device, they would not gain a large number of watts in savings. So the reason it's on the list is because the amount of savings do not justify the DOE actually including them in the law. Some of the other products that are included here, like special impedance, you think that could all open up a loophole. However, the law actually defines the impedance range for the standard offering. And if you look at a typical 75, that's 1.5% through 8%. So to classify yourself as a special impedance transformer, you'd have to be below 1.5 or greater than 8. So for those applications, it's going to be very small in the marketplace and they're excluded. But if you just chose to start specifying impedance, it would not remove it from the law if that impedance falls into the standard ranges. To summarize the slides we just covered, the medium voltage transformers were originally authorized to be looked into in the 2005 Energy Act, and the Department of Energy set the final rule in 2007. The low voltage transformers were in the same act, but instead of letting the DOE set the efficiency levels with the final rule, the efficiency levels were actually called out in the act itself. And medium voltage dry are similar to the liquid. They're in the 2007 rule, with the efficiency levels being set. Because of the lawsuit that was brought to the Department of Energy, we are now redoing the efficiency levels, and this is a moving up the timeline. The DOE always planned to look at distribution transformers again, but because of the lawsuit, they moved it up to have the final rule set in 2013 instead of 2016. The process was a little bit different this time through as well, because the process was actually a negotiation committee instead of an actual process done by advance notices, rules, and public comments. This is a good opportunity for us to check if there's been any questions.
No, Tom, there have not been any questions at the present time.
So to continue, the process for this rule was actually 2 subcommittees. So the Energy Act now allows the Department of Energy to bring stakeholders together and actually have a committee where everybody has a voting right for the efficiency levels. There was 2 committees created, one for medium voltage and one for low voltage. If you look at the list for medium voltage, you're going to see that there's manufacturers, global supply chain, which would be the steel manufacturers, utilities, so the end customers, and then advocates for the environment. And then, of course, the Department of Energy. When you look at the low voltage committee, you're going to see that we're missing the customers. We still have the global supply chain. We still have us manufacturers. You still have the advocates for the environment, but nobody represented the customers in the low voltage process. If the Department of Energy next year actually decides to move forward with looking into the efficiencies even further, we ask that organizations like IEEE and other engineering consultant firms that are national take the time to find if they can send a representative to this process so that the customer base can actually be represented for low voltage.
So the final rule was based on analysis that the Department of Energy found that there are benefits to the nation based on these standards. They will see a less dependency or less, we will reduce our our consumption of energy, which would reduce the burden on our current generation of power. They did see that we would see an increase in cost, but the benefits of the increasing the efficiencies, reducing losses would outweigh the additional costs.
The DOE also found that the available technologies where they set these efficiencies. So the last thing and the most important paragraph in the conclusion from our manufacturing's point of view is the Department of Energy has pushed us to the absolute maximum levels of efficiency with the available technology that's available today. If new technologies become available, they could potentially justify even going further. But at this time, the technology is at its maximum for the manufacturers.
So here is the final rule for liquid immersed distribution transformers. This represents the TSL is the testing standard level that we were evaluated against. The liquid fill immersed transformers finalized on the TSL 1 level. So here's the efficiencies that you can see. The committee settled on the TSL 1 for liquid fill. The adder that we're seeing for the liquid fill transformers is on average of 20% over our current costing today. Remember, that's 2,500 kVA and below. So since the committee did not come to a consensus on liquid fill, they did say that they could look at liquid fill again based on the available technology. There is a variety of core steel called an amorphous core. If that type of core steel becomes more readily available, easier to manufacture, then we could see the DOE would take a look at liquid fill again.
So the low voltage transformers followed a similar process and had testing standard levels. And as you can see, these are the definitions. In April of 2012, the Department of Energy actually told us they were going to set the low voltage levels at TSL 1. Us manufacturers disagreed with that assessment from the Department of Energy. And we made public comments back to them, actually arguing that they go to TSL 2. The steel industry argued to stay at TSL 1, and the advocates for the environment actually argued to go all the way to TSL 4 and 3. When the final rule came out in 2013, the levels that were actually set was TSL 2. Now this did two things. The first thing it did is it put us manufacturing 12 months behind in our strategy. Because in April of 2012, they told us we were only going to have to go to TSL 1. And the TSL 1 allowed us to do it with M6 steel. So the majority of us manufacturers were already using M6 steel for the current offering. When they changed us to TSL 2, which us manufacturers did request, we had to reanalyze how we were going to move forward with the process. So this is one of the reasons you're going to see the data from each of us manufacturers taking a little bit longer to get out to the marketplace, because we are exactly 12 months behind where we could have been if they didn't change the actual rule when they set the final rule. The other thing you're going to see is we went to base levels 3 and 2. Where the liquid field was going to a 0.4 of 1 or a 0.5 of 1, we're actually going all the way to base level 2 and base level 3. Because of that, we're expecting to see an adder in low voltage transformer at 60%. So we're expecting the marketplace to need a 60% increase for low voltage products.
For the medium voltage dry type transformers, TSL 2 was the level that was decided on. This is for our VPI, vacuum pressure impregnated, or a cast coil. We're seeing the adder for the dry type in the range of a 15% adder based on the current levels today, basically going from an M4 to probably an M3 or sometimes an etched core steel that's required. And this, for the dry type, this is where the committee had a consensus. So we don't believe that we'll see the Department of Energy looking at the dry type medium voltage efficiency levels again. So we feel pretty confident we'll be settled with these levels. Again, the TSL 2, sorry, I'm gonna slide ahead, about a 15% adder for the dry type versus what we're seeing on low voltage is a little bit different.
So that was the process and what occurred. This is the actual text from the final rule. And this is critical for you guys when you're writing your specs now, because this is what us manufacturers are required to build the product to after January 1st, 2016. So 431.196, the energy conservative standard and their effective dates. A is low voltage. There are two tables here. Table A, which is what we are building today and can build until the end of the year. And table 2, which is the table that has to go into effect on January 1st, 2016. So if you are specifying a job today, and you know it's going to ship yet this year, you can continue to spec A1. But if you're going to start a job and you know the job's not going to have the transformer ship until next year, we highly request that in your specification you put A2, because that way all of us manufacturers will know that we need to go with the levels for 2016. Another thing that occurred in low voltage that did not occur in medium voltage is we had to go from 3 significant digits to 4 significant digits. This is an extreme burden on us manufacturers because there's a lot of manufacturing processes that add variables. The first being buying the core steel on a roll. The outer level of the roll is going to have different core losses than the inner level of the roll. We then slit that core. We then make the slits into we stack it into a core. We do windings. I believe at least a third of our 60% cost increase is due to the fact that us manufacturers have to design out all those variables. So because we had to go to 4 significant digits and we have to comply, otherwise we're not in compliance with the law, is driving a third of the low voltage cost increase. The medium voltage have been on 4 digits since 2010. Us low voltage were only on 3 significant digits from 2007. So this was a change for our process that is different than medium voltage, and it is driving some of the cost increase.
This is the standard for the liquid fill immersed distribution transformers. Again, table 1 is what we're building to today based on the 2010 efficiencies. Table 2 is the 2016 efficiencies. We can still manufacture the 2010 efficiencies through the end of the year, starting January 1st, required to ship the 2016 efficiencies. So if you do have a project that is still shipping yet this year, you can specify the 2010 efficiencies. If you know it's going to ship next year, go ahead and specify that 2016 efficiency. With average manufacturing lead times, it looks like we're going to be able to ship the 2010 efficiencies through November timeframe, so December, just to make sure that we can fully implement the requirements for the law. We are going to start shipping the 2016 efficiencies actually in December, and you'll see that across the board for most manufacturers. Here's the table for the single phase medium voltage. Same requirements for the table 1 is the 2010 efficiencies. Table 2 is the 2016 efficiencies. Again, effective January 1st of 2016. Here's the dry type medium voltage. A little bit different than the liquid fill. It's based on the BIL of the primary versus just the efficiency of the kVA for the liquid fill. And again, table 1 is for the 2010 efficiencies, table 2 for the 2016 efficiencies.
And I'm checking for questions at the present time. There are none. I'd like to remind the audience that you can submit a question to us by hitting the Make a Request button on the bottom left-hand corner of your screen, and then typing your question in the text box. I'll be monitoring that as we go through this seminar, or as we go through this presentation.
So now we're going to quickly go through form, fit, and functions. We can't go through all of our product offering that is available, but we are going to cover, for low voltage, we're going to cover the 75 kVA and the 300. And for liquid, we're going to cover a 1500 kVA, and for dry, we're going to cover a 1500 kVA. So we'll start with the 75 kVA. And first of all, these are Schneider Electric's form, fit, and function differences. Every manufacturer will have slightly different processes and changes to the offering. Under form, first of all, we have gone to front ventilation only. We have chosen to do this. So we are no longer going to have ventilated openings on our rear of our product. That's going to allow you to move the product to a 1/2 inch from the wall. The other thing we did, based on VOC from our customers, is we've split our terminals. So today all of our terminals were on one terminal bar, and we have chosen to separate them to make it easier for the contractors to decipher which one's the incoming and which one's the outgoing. We've also designed special mounting brackets. If you look at a typical transformer, it has not been redesigned in the base since the 70s. Well, the way you bolt to concrete is not the same today as it was in the 1970s. So we have now created mounting brackets that are external to our units to make it easier to mount the units through concrete with the available technology for how people actually bolt to concrete. If we look at the fit on the 75 kVA, the unit got taller. It also got heavier. The reason it got taller is I reduced my cross-sectional area of my core. When I reduced my cross-sectional area of my core, I did not change the current on the primary or the secondary, and I did not change the voltages. So I had to still get the same amount of conductors through a smaller space. So the only way to reduce my cross-sectional area and still handle the same amount of conductors is to increase the height. We're expecting all manufacturers that had a short unit like ours to have their height increase. If we look at the functionality of the product, the first thing is the efficiencies went up. In this case, it went up approximately 30% at the reference point of 35% loading. So we removed 30% of the losses at that reference point. This unit, our IZs went up, so our let-through went down. That is not the case for the other product in this family. Most of our IZs are going down, which means the let-through current's going to go up. And if you look at this, what this unit is representing, which is the 15 kVA through the 150, what's critical is that the panel's AIC rating doesn't change. That was our goal. We were unsuccessful. We were able to hold the same panel for the 15 through the 112.5, but the 150 kVA we're no longer going to be able to feed a 10 AIC panel due to the change in the impedance. So the majority of the family was unchanged. However, the top kVA size did change, and we do recommend that when you're looking at your new layouts, you verify that the panels you're feeding from these transformers, because the impedance is expected to go down, is still sufficient. The core losses went from 250, oh, I skipped the inrush. In 2007, when we launched our product, all of Schneider Electric's inrushes increased. In this redesign, all of our inrushes are coming back down. So we are now going to be able to feed our low voltage transformer with our full offering of breakers, because our inrush has been reduced on this entire family. The core loss went from 253 to 128. Coil loss from 2518 to 2219. The main portion of that is the BTUs at 75% loading. 5,695 down to 4,695. So we reduced the BTUs on the 75 kVA by 1,000. So your counterpart down the hall that's doing your HVAC, please have him tear up his current tables of rules. It's extremely critical that you get the data from each of us manufacturers and the HVAC starts using the new levels of BTUs and not continuing with the old. Because if they continue with the old, they will be oversizing their systems. The last thing is sound level. These units by default became extremely quiet. We'll be marking all of them for sure at 3 dB, but once we finish our designs, we're hoping to be able to market all of these at 6 dB below. So that was the 75. If we look at the 300, which is going to represent the 225 through 750 and 1,000, under form, fit, and function, under form, once again, only ventilated openings in the front. One of the other things Schneider Electric chose to do is design all these units with an open bottom. Our switchboards at this current level already exist with an open bottom, so we decided at the same similar currents, the 225 through the 750, to design them with an open bottom. That's going to open up your ability to bring in conduits and raceway into the bottom instead of trying to put all the conduits into the side. Once again, we've designed our terminals to meet the National Electric Code. In fact, our primary terminals have been rotated 190 degrees. The reason we rotated our primary terminals 90 degrees is the National Electric Code allows you to size at 125% and 250% for cables. Most of us manufacturers size that terminal at the 125% rule. By me turning it 90 degrees, you now can use both the front and the back. So we've basically given you the ability to meet the 125% rule with its sizing and the 250 by its orientation, because you now have access to both the front and the back of that terminal. We also designed the similar mounting bracket as we did for the low voltage to go with the new technologies for bolting to concrete. Height is the dimension that changed, and of course the weight went up. And the height got increased here for the same reasons that it was increased on the 75. If we look at the data, the efficiency went from 98.6 to 99.02, also a 30% reduction in core loss at that reference point, total losses at that reference point. The IZ went down, but in this unit, even though the IZ went down, the let-through went from 14.1 to 16.8, so the panel did not change. It's still an 18 AIC panel. In this family of offering, the only product line that we had to increase the panel is the 500. So the impedance change on our 500 caused that panel to have to be changed. Core losses from 831 to 479. Coil losses from 6584 to 4674. Once again, the critical thing for your HVAC, BTUs went from 15472 to 10605. So a 5,000 watt BTU reduction. Extremely critical that they do not continue using the current tables. Sound level also decreased on this unit. We will be marketing them at 3 dB, and hopefully we will be able to market them at 6.
Wow, that's a lot of good information for our consulting engineers. Checking on questions. I do not have any questions at the present time. Let's continue.
So let's look at the form, fit, and function for liquid fill. So you won't see a lot of the form or how you'll install this transformer like you saw with the low voltage. So we're going to look at a liquid fill pad mount, but you'll see similar changes for the liquid fill substation. We looked at design line 5, which is a 1500 kVA aluminum 65-degree rise liquid fill transformer. The main thing that we're going to see changing on the liquid fill is the width of the transformer. When we're looking at how we're going to meet these new efficiency levels, we're mainly going to change the grade of the core steel. So we're going to go to a more efficient grade of core steel, but we might need more of that core steel. And what that means is you're going to have a larger coil or core, then you have a larger coil, then you have a wider tank. So your width is going to be impacted mainly on the liquid fill transformer. The depth of the core and coil might be greater as well, but since these are much more efficient, you're going to use less radiators to cool the transformer, so your depth on liquid fill might not change as much. But again, these are all typically engineered to order products, so we do have some standards, but they may vary from kVA voltage range. They're going to weigh a little bit more. You're going to have a bigger core. Those cores are very heavy, so you're going to see the weight of the liquid fill transformers go up. When we get to the function, the efficiency, we're going from 99.42 at 50% load to 99.48 at 50% load. And you can say that's a pretty small change in efficiency, but to get that change in efficiency, we really have to go to that much more efficient grade of core steel. Liquid fill medium voltage, or medium voltage in general, IEEE specifies a standard impedance, so that did not change when you look at the liquid fill medium voltage. So that didn't affect our inrush like you'll see on the low voltage. Core losses went from 1942 down to 1773 watts. Coil losses 10,048 down to 7,944 watts. So again, like Tom said, look at your BTUs. These are going to run a lot cooler. Typically your liquid fill is going to be installed outdoors. We do install some indoor, so that can affect the cooling that's required for your liquid fill transformers. If we look at the dry type, we looked at design line 10, another 1500 kVA, 150 rise, 45 kV BIL on the primary with that 220 degree insulation class. What we're seeing on the dry type, on the VPI style and a cast coil, we are going to get taller. We went from 94 inches up to 100 inches. We are going to get wider. 84 inches was our standard to 96 inches. And we are going to get deeper, 54 to 60 inches. So we saw a lot more impact on the dimensions of the dry type than we did on the liquid fill. This is really going to affect how you're laying out your room. And we saw it really across the board, not just on the 1500 kVA, but most of the 2500 kVA and below, we are going to see the height, width, and the depth grow. This is due to, again, you have that larger core, and on the dry type, a larger core and then your larger coils. You have air insulation, so you're really seeing those coils are spaced wider apart because you have a larger core. That's really affecting your dimensions. And the weight has gone up quite a bit as well. So if you're putting these on a mezzanine, you want to make sure that the mezzanine is built so it can hold this additional weight. These are getting a lot heavier. Efficiency on this particular one, 99.12 to 99.30. And again at 50% load. The impedance again didn't change, so your inrush didn't change. Your losses, the core loss 3,600 watts down to 3,000 watts, and your coil losses 16,500 down to 10,600. And then again, your BTUs greatly decreased. You'll see more of the dry type installed indoor, so when you're sizing your HVAC, based on the BTUs of this transformer, it has gone down quite a bit.
Thank you, Janice, for that great information and good advice. There are no questions at the present time, so let's continue.
So we're going to now cover some National Electric Code updates. So the National Electric Code gets updated every 3 years. However, us manufacturers tend to not to do massive redesigns to our products and the same timeline. Due to this Energy Act DOE mandate, we're expecting all of the changes to the NEC to now be incorporated into the manufacturer's design. So even though us manufacturers might not have changed it because something came out in 2011, with this massive redesign, you should see all the NEC updates incorporated into the marketplace. The first one is that the NEC has changed the 1.2 kV class maximum voltage from 600 to 1,000. This really impacted the wind turbine. Wind turbines are outputting 690 volts. However, the National Electric Code made that be a 5 kV device. So even though you had a transformer that was similar to a 600 volt device, and from a transformer manufacturer perspective was a 1.2 kV class, the National Electric Code required it to be treated like a 5 kV. The last version of the code did change that, so now all those 690 volt units can be treated just like the 600 volts. The other portions of the code we're going to cover is ventilation, grounding, marketing, and terminal bending space. The first is ventilation. The ventilation for transformers for low voltage are required to have a minimum distance specified on each of the units. That minimum distance is set by UL. And UL states that that distance is 6 inches. That's if we heat rise the unit in an open space in the middle of the room. If a manufacturer would like to go less than 6 inches, they have to LCOV test their product. Schneider Electric has chosen to LCOV test this entire product family, which is why we're able to give you the minimum distance of a 1/2 inch. Two things occur while we're doing the LCOV testing. The first is we need to make sure that the transformer is not going to overheat. Well, due to us removing all those coil and core losses, the transformer not overheating is not going to be an issue. The second concern when you LCOV test the product is to make sure that the LCOV walls do not exceed 90 degrees C. Since the National Electric Code is concerned about fire, that's a very critical portion of the LCOV because we know the sheetrock in those walls will be 90 degrees C sheetrock. So we also have to make sure that the sheetrock will not exceed 90 degrees C during this test. We did pass on all of our units as well, so we are able to tell you that on all of our product, there's a 1/2 inch clearance requirement for our product. The next item is 45010. This actually came about in the 2011 code. Dry type transformers and closures now have to have manufacturers give provisions for a ground terminal bar. It's really critical. That is not plural. It's a terminal bar. So if you look at how most contractors install the grounding on transformers today, they bring in the grounding conductor on the primary, they take a lug and they land it. They take a different lug on the secondary and they pull it out. According to the National Electric Code, that is no longer allowed. You have to have one terminal bar. Schneider Electric has been supplying that terminal bar in our mechanical lug kits since this became code. But it was the first opportunity for us to redesign our base and actually supply places for it to be mounted. So all of our units are going to have either 3 or 2 pre-punched holes for this lug to be mounted, where they will be able to meet the bending requirements of those cables and be able to have that one terminal bar mounted. The next area is markings. The code changed in markings, but they didn't change any of the text. This used to be written in paragraph form. Instead of being in paragraph form now, it's now numbered 1 through 8. That's one of the portions that was changed. However, the important portion for low voltage is B, source marking. It basically states you can use the secondary winding as the input as long as you follow the manufacturer's instruction. So us manufacturers are not changing that you can backfeed our units. It's just that the National Electric Code is now more defining how it can be done. And the most important portion is you have to follow the manufacturer's instruction for it to be in compliance with code. All of us manufacturers have given the same instructions for backfeeding units since the 70s. However, most contractors never followed those instructions. And without this bullet, it was hard for an inspector to red tag a unit if the transformer is labeled high voltage and low voltage. Because this is now here, if a product is misinstalled, not following the instructions, the inspectors now have the authority to get it corrected and modified. Terminal wiring space. This was added to the code in 2005. In fact, one of the changes Schneider Electric made in the product we launched in 2007 was moving all of our terminals from low to high in our enclosure. And that was to comply with the 2005 bending requirements. If you look at a transformer that was built in the 90s or earlier, and you wonder how they got the cables in, I wonder the same thing. There was no rules for the bending requirements in transformers until 2005. So that's why you'll see terminals on the older units really close to the bottom where you really don't have the appropriate bending. Since 2005, there has been minimum bending requirements. The minimum bending requirement is greater if you come in the bottom than if you come in the side. And the reason being, when you come in the bottom, the National Electric Code assumes you're making 290s. You got to go in the bottom, you got to make a right or a left to align with the terminal, and then you make your second 90 to go up to the terminal. Where if you're coming in the side, they make the assumption that you're coming in right below the terminals, and there's only going to be 190. So the biggest bending radius requirements is when you're bringing the conduit into the bottom of the transformer. As we continue with low voltage portions, Nema ST20 is the standard that covers low voltage transformers. Sometime between 2002 and 2014, the standard was rescinded. It was rescinded because the manufacturers could not come to a consensus to what needed to be in the standard. Because of that, a large number of specifications started to specify C57-1201 for low voltage. As you can see in red on this slide, 1201 is for 601 volts and above, so it does not cover low voltage product. But because of the gap in NEMA getting their standard updated, lots of consultants needed a standard to give us manufacturers guidance. However, in June of 2014, NEMA finally came to a consensus and they published the new ST20. If you're not using ST20 in your specification for low voltage transformers, we request that you start doing so again. This is the standard that the manufacturers in the marketplace will be following. It is free to download in PDF from the NEMA site. If you want to obtain a hard copy, they do charge for it, but it is available free as a PDF. And we do request that if it's not in your standard today, that you do add it. I actually joke, if a specifier actually does 1201, I tell my TAG organization to state, we're in full compliance. I'm out of scope. I don't have to comply. So it is beneficial to make sure you're using the standard that us manufacturers are building our products to. And this standard does now include sound level. So if you are specifying sound levels for low voltage transformers, this is the appropriate standard to do so. The other standards from NEMA we want to cover is NEMA TP1, TP2, and TP3. These have been in specifications for quite some time. However, in April of this year, I was the NEMA member that suggested that NEMA rescind these. It was immediately second, and it was a unanimous vote by all the manufacturers to rescind these three standards. The reason we are rescinding these standards are the following. TP1 gives a table of efficiencies that we should build to. Because of the law, they're all below the minimum in the law, so it's not a relevant table any longer. TP2 is how we have to test the product. TP2 was a volunteer standard for us to test towards the product. 10 CFR 431 subpart K tells us how I have to test the product to comply with the law. As Janice mentioned earlier, it's a $200 fine per day if we're not in compliance. Us manufacturers are going to test for the law, not a volunteer standard. And lastly, TP3 was in labeling. 10 CFR 429 requires us manufacturers to once a year certify which products are in compliance. It's a readily available document from in the marketplace, so you can obtain from each manufacturer which products are in compliance with the law and how they actually chose to register them. If they chose to use a basic model, if they used to use a KVA family, or if they chose to use an alternate method. So we do recommend if you're using any of the TP1, TP2, and TP3 in your specifications, you change that to 10 CFR 429 and 431 because that is how us manufacturers are building the product.
Yes, we do have a question from John. John asks, is there a new primary and secondary recommended disconnect for the new EX transformers? Also, will it include impedance?
So in regards to the EX product family, Schneider Electric will be updating all their literature for the recommended breakers on their low voltage offering. But when I went through the two designs, the 75 and the 300, the inrush went down in both of those. So the current table is going to work for the EE, that works for the EE, will work for the EX. We'll actually be able to increase the number of disconnects and breakers we have in that table because our inrush went down.
Good to know, Tom. Thanks. I have no other questions.
All righty. See, these next slides are going to cover the low voltage offering. If you recall, we lost a full year on our design table. And there's a large number of specialty offerings for low voltage in the marketplace. So Schneider Electric has chosen to take this opportunity to try to rationalize what we offer and actually give you a better product for a greater value for your applications. The first is how we're going to meet the need of harmonic loads. Schneider Electric has chosen to merge their K-rated family and their harmonic mitigating transformer family into only one offering. The K rating that we have chosen to use is a K9. The reason we have chosen to move forward with a K9 in our offering is, over the last 20 years since K13 became the relevant specification, a number of things have occurred. The first being that the harmonic profile of the devices that were causing the harmonics has been reduced. A prime example, power supplies for computers now have a THD level maximum set by the European norm. That device is made globally. So the amount of harmonics created by a power supply is less today than it was in 1990 when K13 became the level. The other thing we have learned is that the maximum we can get a harmonic load to actually be registered at 100% loading on a transformer is K7. This is also agreed upon by all the harmonic mitigating manufacturers in the marketplace. Their standard specification they recommend is K7 or higher. We agree with them 100%. K7 is the maximum you need to set it at. However, UL 1561 does not let me third-party list the device at K7. They only let me third-party list at 4, 9, 13, 20, and a 30 and 50. So, for us to third-party list the offering, we're going to be forced to go to K9 with the harmonic solution to meet the maximum level of harmonics, which will be a K7. If we're successful in getting the standard change to allow for K7, we will reduce that from K9 to K7 in the future. The other thing we're going to do, which we learned because the harmonic mitigating transformers have become relevant in the marketplace since 2005, is the zigzag secondary is actually more efficient than a delta Y, meaning the harmonics impact it less for losses. So since I'm redesigning my entire product family for an energy act, I might as well offer the product that has the best benefit for hitting those efficiencies. So all of our standard offering, which is today a delta Y for harmonics, will go to a delta zigzag. And if you look at that, the delta Y today is a 30-degree phase shift. If you model the harmonics on the secondary, there are triplins in the secondary. Those same triplins, when you model, show up in the primary. So the K factor has to be higher in a delta Y than a delta zigzag because the triplins are in both the primary and the secondary. Only fifths and sevenths come out, so it did mitigate the harmonic waveform. If you look at a delta zigzag, which is a 0-degree phase shift, which is our direct cross moving forward, the triplin model is only in the secondary. There is no triplins when you model the harmonic waveform in the delta primary phase current. So you can, once again, have a smaller K factor because the triplins are only in one of the two windings. So we will be moving forward with the K9 zigzag secondary for our harmonic solution offering moving forward. If you look at the two efficiency graphs at the bottom of this chart, you'll see that the delta Y is 6/10 less efficient than the zigzag at the 100% load. Alrighty. The next portion that we are specifying is we highly recommend aluminum windings. This has been our stance for a number of years. This is not new, but we always want to remind people that when you specify a copper winding on a low voltage transformer, any of the value you're specifying, I design out. I design all my low voltage transformers via computer programming. I do all my testing with $10,000 meters with 4 probes. So any advantage you think you're going to obtain by specifying a copper winding is going to be designed out by us manufacturers. One of the benefits that you will see when you look at the core and coil is the core and coil will be smaller. However, as a reputable manufacturer, I want to always give you the ability to value engineer your job. So if I made my copper units physically smaller than my aluminum, and you all of a sudden had a tight budget, you would not be able to swap them out. So even though I can make the copper unit smaller, we choose not to, and that choice not to is actually more beneficial in the marketplace because it gives you more flexibility if you do have copper windings on a job to VE that opportunity when required. If we did actually make copper units smaller, that would go away. The next item is electrostatic shielding. This is the standard specification that every manufacturer complies with for an electrostatic shield. It's actually verified via DC testing. I know it's a DC testing because I did it when I was a co-op in 1991. Transformers are not DC devices. However, DC verification testing is how they prove that the shield actually functions per this specification. Technology does allow us to actually test the shield underneath full AC conditions. When you test the shield under AC conditions, you're going to find the following. If you leave the secondary ungrounded, the shield's going to give you all those benefits that are in the specification. However, if you ground the secondary, which is you remove that coupling capacitance from the circuit, the shield has no value whatsoever. Since 95% of all low voltage transformers are going to be grounded because of the National Electric Code requirements, shielding is really a specialty offering for a specialty application. It should not be the standard or the norm in any specification, because we can now AC test for it, and when doing the AC testing, you do find that when the secondary is grounded, the shield has no value. The last slide we're going to discuss is, should we be specifying better than the law? If you recall, when we actually had the conclusion from the law, we pointed out that the DOE determined that we were at the maximum efficiencies that was economically justified for the available technology. In 2007 through 2006, the NEMA premium in the CSL3, which came from the DOE's 2004 research, actually was a justifiable level. In fact, it is what the law is going to be on January 1st, 2016. So the product that was being specified above the current level was justifiable for the last 9 years. However, moving forward, first of all, there is no research from the DOE above and beyond the law. In fact, the DOE did 10,000 designs at each design level to determine that the levels they were setting is the most efficient. The other thing the DOE did is that analysis was not at the 35% point of law, it was at where the product was being loaded. So it's actually taking the analysis at the 10 to 15 or 10 to 25% loading points to also come up with that reference point. Even though Schneider Electric fought for higher levels of efficiency during the public notices, we are recommending you do not go any higher until there's actual research to justify going levels above. The first research that needs to be done is there's a new baseline on January 1st, 2016. All of the research that's done so far compares EL3 with EL0 and EL4 with EL0. EL0 is now either EL2 or EL3. So any benefits you might see are going to be reduced drastically because the law's base point has been moved up. So until that research is done, and hopefully done by an independent party like the Department of Energy or the Environmental Protection Agency, we do not recommend you specify anything above the law moving forward.
Our lines are open for questions. If you have any questions, please use the make a comment in the bottom left-hand corner. At the present time, we have no additional questions. Tom and Janice, you've done an excellent job of delivering that highly technical, complex information, as I say. Are there any comments that you would like to make in summary?
I guess, in summary for the medium voltage, know that our dimensions are changing for when you're sizing your rooms. The BTUs are lower when you're sizing your HVAC. We can supply these transformers today, but we will be ready to supply these transformers, of course, starting January 1st of 2016.
In summary of the low voltage, the height is what went up. The weight also increased. It's extremely critical that you verify that the IZ did not go down to the point that changed your AIC level of the panels you're feeding. BTUs went down, so please make sure that your counterparts do remove their current tables and set new tables. And lastly, Schneider Electric's product will be available during the last quarter of this year. So if you have any customers that want to be early adapters, we will be able to meet that need starting October 1st with the new offering. And then, of course, at the beginning of the year, it will be available from our warehouses. Well, thank you guys for your time.
We do have a couple questions that just came in, Tom. One of them, DOE 2016 is for shipments in the US only?
So the law is for the United States only. Any place outside the United States is covered by those countries. 429, so 10 CFR 429 states that if I build it in the United States and I know it's going external, I have to label it not for use in the United States. So if you have a job outside the United States, you specify that product. It can be built inside the United States, it can be shipped inside the United States, but it's going to have a label on it that states not for use in the US, which means it's not in compliance with the law, it's expected to be exported. And that's for both medium voltage and low voltage. We both have to comply with that labeling.
We do see some US customers, though, if they have sites that they are exporting for their projects, some do want us to comply, even though if it's for a US-based company and it's going somewhere overseas. They sometimes do still specify the US requirements.
Here's a follow-on question. Is there a deduct available for it in the product selector?
There will be. So for medium voltage, we're working on updating our selectors right now. And for a time period, we will allow you to select the 2016 efficiencies to adopt early if you choose. And then once we move all of our base designs to the 2016 design, for a short period, we will allow you to select the 2010 efficiencies until we are fully implemented. If you are shipping an exported product outside the US, we do offer what we call an IEEE international standard, and when you pick the international standard, it will allow you to select the 2010 or no DOE efficiency requirement at all.
And for low voltage, using the same selector, so at the end of the year, actually on October 31st, the EE selector will be shut off for the United States. It will be continuing to be allowed in Canada and Mexico so that they can continue to have those offering. The rest of the world normally requires 50 hertz for low voltage, so that's how they're normally chosen for export, is via our 50 hertz option in our selector. So in regards to having a deduct when it's going to be exported out, it's not really a deduct. You're just going to be continuing to price it up as the old family. And the new family would only be chosen if you chose to have those level of efficiencies for where your job is landing.
Thank you for those answers. And thank you for your time. Thus, this ends the webinar, but please note that if you would like to download the webinar itself, the PowerPoint presentation, go to the top right-hand corner of the screen and download the presentations document. To get your certificate of attendance, please log into our Consulting Engineer Schneider Electric portal and follow directions on it to the training on the top corner and select this particular webinar, and you'll be able to download a document or for certificate of attendance to meet your PDHs in many cases. Thank you, and have a great day.